Now, China has a problem. Its 3 astronauts are stranded in space, and the Chinese astronauts were scheduled to return to Earth after 6 months. But now their return capsule is damaged. Chinese Space Agency says that it was struck by the orbital debris.
In November, 3 Chinese astronauts faced a nightmare few could imagine. Their return capsule, meant to bring them safely home, may have been struck by high-speed debris.
Safely back home after their return capsule touched down in the Gobi Desert.
With re-entry now a life-or-death gamble, engineers on Earth scrambled to devise a plan. Every second mattered, and every decision carried the weight of human lives. For 16 tense days, the world watched as China orchestrated a daring orbital rescue that would test the limits of spaceflight and expose weaknesses in NASA's approach. Pending re-entry disaster. On April 24, 2025, China launched Shenzhou 20, a crewed mission bound for the Tiangong space station. The spacecraft lifted off from the Jiuquan Satellite Launch Center aboard a Long March 2F rocket, beginning what was expected to be a routine 6-month stay in orbit. The crew included mission commander Chen Dong, along with astronauts Chen Zhongrui and Wang Jie. During the flight, Chen Dong passed a major milestone, becoming the first Chinese astronaut to spend more than 400 total days in space.
Chinese astronauts, also known as taikonauts, have arrived at the Tiangong space station and completed China's first ever crew handover in orbit. The new team's expected to remain in space for 6 months.
By the end of the mission, the crew had logged 204 days in orbit, setting a new national record for the longest single in-orbit stay by a Chinese crew. For months, the mission appeared to progress without incident. Daily operations continued as planned, and there were no public signs of trouble. That changed shortly before the crew's scheduled return in early November 2025, when engineers raised a serious concern. Data suggested the return capsule may have been struck by high-velocity space debris, possibly damaging a critical component and making a standard re-entry unsafe. If confirmed, this would force the first alternative return in the history of China's space program. The concerns centered on the return capsule, the part of the spacecraft responsible for bringing astronauts safely back to Earth. During re-entry, this capsule must survive one of the most extreme conditions any vehicle faces. Even a flaw that causes no problem in orbit can become deadly once the spacecraft enters the atmosphere. As the capsule descends at several miles per second, it compresses the air ahead of it into superheated plasma, creating a wall of fire that can exceed 2,000 degrees Celsius. The heat causes rapid and uneven expansion across the capsule's surface. If a window or panel is already damaged, that expansion concentrates stress along the weak point, allowing cracks to spread instantly, an event no crew could survive. Heat, however, is only part of the danger. As the spacecraft plunges lower, outside pressure rises sharply, while the cabin remains pressurized to keep the astronauts alive. Any crack becomes a structural failure point. The pressure difference could cause sudden collapse, triggering explosive depressurization. Superheated gases would surge into the cabin, destroying life support systems and the interior within seconds. Under those conditions, a normal return was no longer possible. Instead of coming home as planned, Shenzhou 20's 3-person crew remained in orbit for an additional 9 days, sharing the space station with another trio of astronauts who had just arrived aboard Shenzhou 21 at the end of October. So what exactly happened to Shenzhou 20, and how was its crew going to make it back to Earth?
Shenzhou 21 commander Chen Dong described their 6-month mission at the Tiangong space station as success.
Space patch-up job. With the Shenzhou 20 crew confined aboard Tiangong, the immediate critical responsibility fell to engineers at the China Manned Space Engineering Office to design a safe rescue plan. As the investigation progressed into what officials described as a rigorous expert analysis phase, the focus shifted. The question was no longer whether the spacecraft had been damaged, but how severe that damage truly was. To reach a definitive answer, the conditions in orbit had to be accurately recreated on Earth. Using high-resolution images and precise measurements sent down by the taikonauts, technicians constructed a replica of Shenzhou 20's damaged window. One of the greatest challenges was reproducing the crack's accurate geometry. Its atom-thin shape was critical, as even subtle differences could drastically affect how stress would concentrate at the crack's tip during atmospheric re-entry. Once the replica was complete, it was subjected to a battery of tests meant to replicate the brutal conditions of re-entry. Engineers ran multiple simulations to explore worst-case scenarios and identify how the damage might behave under extreme stress. Among the most critical were wind tunnel ablation tests. Inside specialized facilities, the window replica was blasted with plasma jets, recreating the multi-thousand-degree temperatures and hypersonic gas flows a returning capsule would endure. Throughout these tests, sensors and high-speed cameras closely monitored the crack for any signs of growth or sudden failure. Additional trials applied mechanical stress to simulate violent vibrations and intense gravitational forces experienced during deceleration. Each experiment was designed with a single goal: to determine the exact breaking point of the compromised component. The risks were extreme. The inner glass could fail, costing lives. The crack could rapidly expand and blow out the viewport, or the entire window structure could collapse altogether. Every scenario led to the same outcome: loss of the crew. Faced with even the slightest chance of a lethal failure, the China Manned Space Agency made a clear and decisive call. Human life would come before hardware. Rather than gamble on a damaged spacecraft, officials scrapped the original return plan and turned another Shenzhou vehicle into an emergency lifeboat. Time was running out, and Tiangong, while capable of hosting 6 people, could only do so briefly. The station is designed to sustain a crew of 3 for 6 months, not double that number. So, on November 14th, the Shenzhou 20 crew boarded Shenzhou 21 and returned safely to Earth. The move worked, but it came with a serious consequence. That left the newly arrived astronauts aboard Tiangong without a return vehicle. What happened next?
After returning home aboard the Shenzhou 21 spacecraft, I feel truly at ease. The path of human space exploration is not smooth. It's filled with difficulties and challenges.
The escape pod. With the newly arrived Shenzhou 21 crew now aboard Tiangong without a return spacecraft, China moved quickly to stabilize the situation. Engineers and mission planners immediately began preparing a replacement Shenzhou vehicle for launch, accelerating timelines that are usually planned years. The station could not remain without a guaranteed way for its crew to return safely. At the same time, a second problem became impossible to ignore. The damaged Shenzhou 20 spacecraft was still docked to Tiangong. Since China began long-term station operations in 2021, every Shenzhou mission has followed a strict pattern, with a crew of 3 rotating every 6 months. Never before had a Shenzhou capsule been left in orbit while its crew returned home aboard a different vehicle. This created an entirely new challenge. If the damaged spacecraft remained attached, it would block future missions. Tiangong relies on having at least one docking port available at all times for crew rotations and emergency access. Leaving Shenzhou 20 in place without a plan would eventually bring operations to a halt. The response came quickly. On November 25th, Shenzhou 22 launched uncrewed, nearly 6 months earlier than initially scheduled, and docked with Tiangong later that same day. Its arrival restored a flight-ready return vehicle for the astronauts currently aboard the station. However, it also filled the final available docking port, making it clear that Shenzhou 20 would need to be removed before the next crewed mission, Shenzhou 23, could arrive in 2026. Shenzhou 22 also carried fresh food, clothing, and essential supplies to replace those used during the extended stay caused by the earlier emergency.
Includes China's youngest astronaut, and the combined teams also enjoyed what they dubbed the first barbecue in space.
In addition, it delivered specialized equipment designed to help engineers determine whether the cracked window on Shenzhou 20 could be repaired while still in orbit. For the time being, officials announced that the damaged spacecraft would remain docked to support inspections and experiments related to the incident.
What was your reaction when you heard that there was a crack in the window?
These cracks could fissure and get larger, and under this extreme heat.
If the damage proved impossible to fix, the plan would shift toward undocking the capsule and guiding it into a controlled re-entry over a remote region of the Pacific Ocean. China later confirmed that deorbiting the spacecraft was already part of long-term planning.
Chinese authorities say an emergency plan has been activated and the damaged Shenzhou 20 ship is likely to return to Earth without a crew.
On December 9th, astronauts Wu Fei and Zhang Lu conducted an 8-hour spacewalk to visually inspect the damage firsthand, providing critical data to engineers on the ground.
Chinese astronauts on the Shenzhou 21 mission conducted an 8-hour spacewalk outside the Tiangong space station on December the 9th.
This was the second time in just 2 years that astronauts were left aboard a space station without a dedicated return spacecraft. Still, the other incident unfolded under far more dangerous conditions. What happened next was anything but seamless. The Starliner disaster. In June 2024, NASA astronauts Butch Wilmore and Sonny Williams launched aboard Boeing's Starliner, bound for the International Space Station for what was meant to be a routine 10-day mission. The capsule launched properly and reached orbit as scheduled, but engineers detected problems almost immediately.
NASA has scrubbed plans to launch Boeing's version of an astronaut taxi into space.
Multiple helium leaks and malfunctioning thrusters. Helium is critical for delivering fuel precisely into the engines. Without it, the spacecraft's trajectory could fail, making re-entry unpredictable and potentially deadly. Returning at the wrong angle or with compromised thrusters risked overheating, structural failure, or total loss of the capsule. NASA decided to return the Starliner to Earth uncrewed, but left Wilmore and Williams stranded aboard the ISS, hundreds of kilometers above Earth, with no immediate way home. What was meant to be 8 days in orbit turned into months.
It's supposed to be an 8-day mission, and seeing as they're now coming back next February, it's going to be 8 months. I mean, that is a really long...
The astronauts were forced to adapt to life in space, confined to the station's tight quarters and entirely dependent on life support systems. Eventually, in September 2024, a SpaceX Crew Dragon capsule arrived at the ISS, fully operational and ready to bring the astronauts home.
The SpaceX Crew Dragon capsule has successfully docked. Return of astronauts Butch Wilmore and Sunita Williams.
17 hours later, the astronauts were safely back on Earth after 9.5 months stuck in space. According to space analyst Osberg, both the Boeing Starliner crisis and China's Shenzhou incident were strokes of luck, fortunate outcomes in situations that could easily have ended in disaster. Yet, even with rapid responses and expert planning, the world's top space agencies still lack a proper international rescue system, one capable of acting instantly when astronauts are stranded hundreds of kilometers above Earth. And history has shown us painfully that we've learned this lesson the hard way. Lessons from the past. Going to space has always been dangerous, but the early Apollo program made the risks painfully clear. In the mid-1960s, NASA was racing against time to meet President John F. Kennedy's goal of landing a man on the moon before the decade's end.
We shall send to the moon 240,000 miles away from the control station in Houston.
Engineers worked at a breakneck pace, developing the technology needed not only to reach the moon, but also to establish U.S. dominance in space, conduct lunar science, and enable humans to work safely in the harsh lunar environment. By 1966, NASA had upgraded its Saturn I rocket to the more powerful Saturn IB, which would carry the Apollo spacecraft, known as the Command Service Module, or CSM. The command module was the astronauts' lifeline, designed to take them safely to space and back to Earth. Inside, just 6 cubic meters of space contained 3 compartments, operational displays, crew couches, and all necessary equipment, leaving very little room for movement. The first human-crewed mission, Apollo 1, was set for February 21, 1967. Its purpose was to test launch operations, ground tracking, and the performance of the Saturn IB and the CSM. The crew consisted of veterans Gus Grissom and Ed White, alongside rookie Roger Chaffee. Grissom had flown Mercury missions and narrowly survived a hatch malfunction on splashdown. White was the first American to conduct a spacewalk, while Chaffee was eager to prove himself as a full-fledged astronaut.
First American astronauts land on the moon, and they're scheduled to at the end of next year. They'll travel in a spaceship exactly like this.
From the start, concerns surfaced. The crew noted the abundance of flammable materials in the cabin. Engineers and astronauts also raised alarms about frayed wires, potential short circuits, and the inward opening hatch that lacked explosive bolts for rapid escape. In the push to meet deadlines, NASA had chosen a pure oxygen cabin atmosphere to reduce weight. But this choice magnified the danger. Even a small spark could ignite a deadly blaze. On January 27, 1967, the crew entered the capsule for a plugs-out test, a final rehearsal before launch. Problems appeared immediately. Foul odors from the oxygen tank, alarms triggered by high oxygen flow, and persistent static on communications foreshadowed what was to come. Then, at 6:31 p.m., a flash fire erupted inside the cabin. Flames and toxic smoke engulfed the astronauts in just 30 seconds, far faster than the 90 seconds needed to execute emergency procedures.
It was an explosive combustion. The hull of the spacecraft had ruptured from the pressure of the fire.
Ground crews battled to open the hatch, taking 5 agonizing minutes. Grissom, White, and Chaffee did not survive. A few years later, space would remind the world of its unpredictability. Skylab, America's first space station, faced an entirely different kind of crisis. When the final crew departed on February 8, 1974, they left the station in orbit at 269 by 283 miles. Operators at NASA's Johnson Space Center ran final system checks, vented the atmosphere, and turned off the power. Based on solar activity predictions, scientists estimated the station would remain in orbit until 1983. But the Sun had other plans. Higher than expected solar activity expanded Earth's atmosphere, increasing drag on Skylab. Its orbit began to decay faster than anticipated, and by 1977, projections suggested re-entry could occur as early as mid-1979. Plans to revisit the station with the space shuttle were delayed, making a controlled reboost impossible. Skylab, at 169,000 pounds, would become the heaviest spacecraft to re-enter at that time, and engineers knew some debris could survive the descent. Avoiding populated areas remained a priority. In 1978, NASA reactivated Skylab, controlling its attitude to slow orbital decay. Using limited communications through 5 ground stations, controllers carefully adjusted the station's orientation, first into the end-on velocity vector minimum drag attitude. This maneuver extended its life by roughly 3.5 months, but delays in the shuttle schedule made saving Skylab increasingly unlikely. By December 1978, NASA officially canceled the shuttle reboost mission, shifting focus to minimizing risk during an uncontrolled re-entry. As Skylab continued its descent, operators made precise adjustments to control its path. On January 25, 1979, they shifted the station into its solar inertial attitude to keep batteries charged, then, in June, moved it into a high-drag torque equilibrium attitude to better guide its final trajectory. The goal was to ensure re-entry over mostly ocean and sparsely populated land. On July 11, 1979, Skylab's final orbit began. After passing over North America, the station flew southeast over the Atlantic, around the southern tip of Africa, and northeast across the Indian Ocean toward Australia. At 93 miles altitude, controllers initiated a slow tumble to target the entry point. Beyond this, the ground lost control. As Skylab plummeted, tracking stations observed its large solar array detaching. The station broke apart at roughly 10 miles above Earth, slightly lower than expected, shifting the debris footprint eastward. Western Australia felt sonic booms as fragments fell across the outback.
Yeah, exactly. This is a pretty substantial hunk of metal, and it was on fire when it hit the ground.
The final footprint stretched 2,450 miles, though most debris landed safely in uninhabited areas. Today, a museum in Esperance displays recovered pieces, including an oxygen tank and a titanium container. The lessons of Apollo, Skylab, and the shuttle about in-space rescue are fading, just as more people from more countries and commercial spacecraft are heading into orbit. Some agencies have already stepped up to fill this critical gap. The grand plan for space rescue. For decades, engineers have explored the idea of rescuing a stranded crew in orbit. The concept is simple. Astronauts face danger only if both their main spacecraft and a backup rescue system fail. In theory, even a spaceship that is only 90% reliable could offer a crew a 99% chance of survival if paired with a rescue system that also works 90% of the time.
Or maybe SpaceX could step in to help with a rescue mission.
The stakes are high because improving spacecraft reliability is expensive,
costing up to an astonishing $150 billion.
Achieving 99% reliability costs a lot, but pushing it to 99.9% is far more costly. NASA has even considered launching crews on rockets with reliability as low as 77%. With a dependable rescue system in place, survival odds can rise dramatically, sometimes to nearly 100%. There are two main approaches to space rescue. One treats the backup like a lifeboat, a small craft for everyone to climb into for the journey home. The challenge is packing enough people and life support systems into something so compact. The second approach is more individual. Each astronaut uses a personal device to leave the spacecraft. But a person-sized system must survive extreme heat, pressure, and speed during re-entry while keeping the astronaut alive. Both approaches carry immense engineering challenges. Fortunately, all recent incidents have occurred after crews reached safe havens, such as the International Space Station. If trouble strikes before a spacecraft reaches a station, the situation is far more dangerous. Most current rescue plans rely on self-rescue. The crew must save themselves using onboard equipment. Sending another spacecraft to help is difficult because the damaged vehicle must sustain its crew long enough for rescue, and the backup must launch quickly, despite weather or orbital constraints. Rescue is easier when a spacecraft can dock with another that already has life support. Apollo 13 is a classic example. The lunar module served as a temporary lifeboat until the crew returned safely.
The team that was trained to handle emergencies like that and like many other things.
In low Earth orbit, astronauts may use the ISS as a refuge, but only if the troubled spacecraft can adjust its orbit to reach it. For instance, the Columbia shuttle could never have reached the ISS after launch because its orbital tilt required more fuel than it carried. Some vehicles are naturally suited to emergency rescue. SpaceX's Dragon is highly reliable, while Russian Soyuz capsules are quick to launch, work in nearly all weather, and can remain docked for months, ready to bring a crew home. The space shuttle could carry more astronauts, but required more preparation and better conditions, making it slower to respond. Rescuing a whole shuttle crew might require multiple Soyuz launches, complicating logistics and increasing risk. Every space rescue plan is a balance between acceptable risk and cost. Rescue systems are expensive, complex, and challenging to test. When main spacecraft programs run into budget or technical limits, rescue requirements are often questioned. It is better to make the primary vehicle more reliable than to spend on a backup. Comparisons to airplanes are common. Early planes carried parachutes, but modern airliners do not. Critics suggest astronauts could go without rescue systems too. But human spaceflight is far riskier than aviation. The technology is new, flights are fewer, and spacecraft operate under extreme conditions. Rockets carry enormous fuel loads, travel at incredible speeds, and must be as light as possible. Even walls are often thinner than a soda can when scaled down. In space, any leak is dangerous. Materials behave differently in a vacuum, and temperatures swing from blazing sunlight to freezing darkness within inches. During launch, vehicles face intense aerodynamic forces. During re-entry, the exterior can heat to a temperature hotter than molten metal, while air pressure strikes with crushing force. In orbit, debris and radiation add further hazards, capable of damaging windows and radiators, as seen with the Space Shuttle, and more recently with China's Shenzhou 20. Thankfully, China already had plans in motion for a new spacecraft capable of dramatically improving crew safety, a design that could redefine space rescue for the future. China's future of space travel. China is preparing to launch a new era of human spaceflight. According to the China National Space Administration, the next-generation crewed spacecraft, Mingzhou-1, is set to fly in 2026. This vehicle represents a major leap forward from the aging Shenzhou series. Unlike its predecessors, Mingzhou is designed as a flexible, modular spacecraft capable not only of ferrying astronauts to low Earth orbit, but also of supporting eventual lunar missions. The spacecraft consists of two primary components: The crew module is designed to safely return astronauts to Earth, while the disposable service module manages propulsion, power, and life support during the mission. This separation allows the crew module to be partially reusable, with detachable heat shields that can withstand multiple flights. Fully assembled, Mingzhou stretches nearly 8.8 meters long and weighs around 21,600 kilograms. Its capacity is adaptable. It can carry 6 astronauts or 3 astronauts plus approximately 500 kilograms of cargo. This modular approach allows mission planners to tailor each flight to specific objectives, whether transporting crew, science experiments, or essential supplies. Mingzhou is intended to serve as China's primary crewed space vehicle for decades. When paired with the Lunar lander, it will support crewed missions to the Moon, beginning as early as 2030. The first flight of the Mingzhou 1 will launch atop the Long March 10A rocket from the Wenchang Space Launch Site on Hainan Island. After reaching orbit, it will dock with the radial port of the Tiangong Space Station's core module. The mission will test the spacecraft's systems, deliver scientific instruments, and transport supplies, and experiment payloads for applied research. Development is nearing completion, and the spacecraft has already undergone critical safety evaluations. On July 17, 2025, CNSA conducted a zero-altitude abort test, also known as a pad abort. Using a test article of Mingzhou at the Jiuquan Satellite Launch Center, engineers simulated a launch emergency. A command severed the capsule from a dummy service module, igniting the vehicle's launch escape motors. 4 main motors pulled the capsule away, while a smaller motor with 8 nozzles managed directional control. Within 20 seconds, the capsule separated and stabilized for descent. Drogue parachutes were deployed first to slow the descent, followed by 3 main parachutes to ensure a gentle landing. Finally, the heat shield detached, allowing landing airbags to inflate. This test was critical for confirming the safety of future crewed flights. The next phase will be an in-flight abort test, designed to replicate conditions similar to NASA's Orion or SpaceX Crew Dragon abort tests. Meanwhile, China's development of supporting technologies continues. The Long March 10 rocket and a crewed lunar lander are both progressing steadily, with additional tests scheduled. In the near term, Mingzhou is expected to perform missions to the Tiangong Space Station, transporting up to 7 astronauts on the Long March 10A. Eventually, the spacecraft will carry 3 astronauts to the Moon on the Long March 10. China is not only advancing crewed spacecraft, but also transforming its orbital cargo capabilities. In 2023, CNSA issued a call for proposals for a low-cost cargo transportation system for Tiangong. The spacecraft had to be flexible, reliable, and cost-efficient, capable of delivering between 1.5 and 8 tons of cargo, providing at least 7 cubic meters of pressurized space, docking with the station, and remaining attached for up to 3 months. The system also needed to return 2 tons of waste to burn up in the atmosphere. On October 29, 2024, CNSA announced 2 winning designs: the reusable Haolong shuttle and the versatile Qinghao spacecraft. Both are entering the flight verification phase. The Haolong shuttle is a compact, reusable cargo vehicle developed by the Chengdu Aircraft Design and Research Institute, the same group behind several Chinese fighter jets. With an 8-meter wingspan and a length of roughly 10 meters, Haolong draws inspiration from the space shuttle while remaining far smaller, comparable to the US X-37B or China's Shenlong spaceplane. Fully autonomous, it launches atop a commercial rocket, operates in orbit, docks with Tiangong, and returns to Earth to land like a conventional airplane. Once on the ground, it can be serviced quickly and prepared for the next mission. Haolong dramatically expands China's cargo return capabilities, which have historically been limited by the Shenzhou capsule's small cargo capacity. The second cargo spacecraft, Qinghao, represents a different approach. Developed by the Innovation Academy for Microsatellites under the Chinese Academy of Sciences, Qinghao debuted as a life-size model on China's Space Day in April 2025. Unlike traditional dual-module cargo vehicles, Qinghao integrates propulsion and cargo into a single capsule. The design maximizes usable space while keeping the system compact and efficient. The interior features 27 cubic meters of cargo space arranged in a 4-tier shelving system with 40 compartments for specialized items. It can transport up to 2 tons of supplies, including crew necessities, scientific experiments, and delicate cold chain goods. Qinghao is also highly automated. High-definition cameras and onboard visual algorithms track inventory, automatically recording when items are removed or replaced. A voice-activated search system helps astronauts quickly locate packages. Its modular refrigeration system holds 300 liters of cold chain goods, allowing precise temperature control for perishable items. Qinghao can deploy small satellites and operate science payloads in orbit, giving it multi-mission capabilities. For its first flight, Qinghao will launch atop the Legion 2 reusable rocket, developed by CAS Space. This liquid-fueled rocket can deliver between 8 and 12 tons to orbit and is designed for multiple reuses, forming part of China's growing low-cost launch infrastructure. Qinghao and Legion 2 were co-designed to function as a cohesive system, ensuring efficient, reliable transport for Tiangong missions. Beyond immediate crewed and cargo operations, China is exploring experimental space technologies with long-term strategic potential. Quantum communication satellites like Mikius and Jianong-1 aim to create highly secure orbital communication networks. Spaceplanes like Haolong, along with space-based AI and computing systems, are part of China's vision for a technologically advanced orbital presence. The three-body computing constellation, set to grow to nearly 3,000 satellites by 2030, could serve as a massive orbital supercomputer, while space-based solar power projects such as Chasing Sun and the so-called Three Gorges Dam in space aim to provide constant renewable energy. Finally, China is researching nuclear thermal propulsion, which could significantly reduce travel times for deep space missions. Early prototypes suggest this technology might one day shorten a round-trip Mars mission from years to months, though the work remains experimental. China's investment in Mingzhou, Haolong, Qinghao, and these experimental technologies shows a comprehensive vision for space. The country is building a flexible, modular, and scalable system for crewed missions, cargo transport, lunar exploration, and long-term technological advancement. The combination of reusable spacecraft, automated cargo systems, and cutting-edge research shows a deliberate, forward-looking strategy to strengthen China's role in human spaceflight and orbital operations. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.